Good morning, everyone, and thank you for joining us today for the AI Predictive Maintenance and Process Optimization webinar. We're very fortunate today to have our founder and group CEO, Trevor Bloch, with us. He's going to be giving you a look under the hood of the VROC AI solution and how it can help your business moving forward. Now, the presentation is going to last approximately 25 minutes, and then we're going to open up to a Q&A at the end for about 5 minutes. If you do have any questions, then if you could please direct them to the box on the right, the chat box, which is just here. You should see a short message that just came up for myself there. And without any further wasting of time, I'm going to pass over to Trevor and let him get straight into it. So take it away, Trevor.
Perfect. Thanks, Jonathan. Hello and welcome to today's webinar on predictive maintenance, empowering your remote operations. And I guess in today's climate, optimizing your operations, reducing OPEX, increasing production is critical, especially in the oil and gas industry. I mean, we've all seen what's been happening with the oil price over the past few weeks. So this is why technologies such as predictive maintenance are becoming so important. Personally, I think that when this pandemic is over, it may not be business as usual, and it may be businesses that embrace new technologies such as this one, such as the remote working that most of us are also doing at the moment. Those businesses will be the real winners and the ones that survive. As John mentioned, if you have any questions, please enter them in the chat. I'll try and answer them during the session, or we'll get to them at the end. So I'm just going to bring up a few slides just to take you through what we're doing and how this AI predictive maintenance actually works. And I guess the first question is, why are we actually doing this? Why are we using, what's the big deal about predictive maintenance and AI in an industrial context? And I guess the reason is, if you look at some of the management consultants that have been doing reports over the past few months, admittedly, some of these were when the world was in a much different place, but you can see that McKinsey is saying that this sort of tech is going to add $13 trillion in value to the global economy. And companies such as EY are saying that predictive maintenance is going to have a transformative effect on industry. So we're not talking about incremental changes here. We're talking about a step change in the way that people do things and a step change in the operational effectiveness of these facilities. So these are some of the reasons why this technology is so important at the current point in time. And so I guess one question that we often get asked is, how does all this work? How do we deploy this technology and what does it actually do? And this is a bit of a diagram to describe some of how that works. And if we just follow this diagram from the top left in a clockwise direction, we can see that we take your existing monitoring sensors from your assets or data historians, and that's the key data that we're using to run these sort of systems. There's no need, in an industrial context, there's no need for new sensors or new equipment to be installed. Generally, most industrial facilities have sufficient sensors and sufficient data to make use of this technology just using the assets and the infrastructure that they already have. So we take the data from your existing assets or data historians, and that data is sent along via secure communications to a big data center. And this data center might be, for example, a VROC private data center. It might be your own data center on site, or it might be your own public cloud infrastructure, such as Amazon Web Services or Azure. And so what we do is we get generally the past 12 or 24 months worth of data. We feed that into the data center, and then we set up some live streaming, so we get live real-time data coming in at the same time. And once we have this 1 or 2 years worth of historical data, we can start running AI over that data set. And the advantage of using AI in this context is that the AI is able to learn how your plant works under all sorts of different operating conditions. So by looking at the data and by looking at how your plant is operating, it can learn what it looks like when your plant's running at optimum capacity. It can learn what your plant's looks like when it's not running at optimum capacity, when there are failures imminent, and when there are undesirable events like flaring events occurring. So the AI is processing all the sensor data from your facility and building models as to how this facility works under all these different operating conditions. And so once it's got a good understanding of holistically how this whole facility works, it can start providing insights into predicting when certain undesirable events are going to happen. So prior to equipment failing or production degrading, the AI can see small signs indicating that these events might be occurring and can alert you ahead of time that they may occur. And it can also tell you what the root cause of that event is. So you can repair or make the necessary changes to prevent that undesirable event from occurring. Of course, once we've got all the AI models running, they're presented via user configurable web dashboards to either on-site or off-site personnel, onshore or offshore, to be able to configure and view the data in a way that's conducive to the way they like to work. And I guess when you look at the way that, I'll go through a few solutions, that we deliver first, just before I get on to how we do it. But VROC has two main solutions. We have predictive maintenance and process optimization. They're both generally delivered at the same time. But for us, predictive maintenance is identifying the time to failure. So it's identifying when a certain undesirable event is going to occur. So I want to predict when my compressor is going to fail next. I want to predict when my production is going to be below my expected production rate. I want to predict when my next flaring event might happen. I want to predict that before it happens, and I want to identify the cause of that failure or the cause of that undesirable event so I can avoid it, and I can make the necessary changes to avoid it before it actually happens. So that's what we call predictive maintenance. Process optimization, on the other hand, is identifying system anomalies and system degradation. So if the AI has had a look at your data and has understood that your plant can run at a certain capacity, it has a certain optimum capacity. If we're not running at that optimum capacity, if our production rate is lower than expected or the quality of our product is lower than expected, we want to know what's driving that. Why is my production rate so low? Why is my product quality lower than I expect? And what do I need to do to bring it back up to an optimum level? That's what we call process optimization, or that's what we term process optimization. For today's webinar, we're going to focus on predictive maintenance, but we'll most likely do another one in future to look at how process optimization works as well. So if we're focusing on predictive maintenance, we can see that there's a number of standard ways that these solutions are deployed in industry at the moment. Most organizations have tried a predictive maintenance project and they've run one or two problems through a data science team and got some good results. But the problem we find is that scaling those results from one or two problems to 50 or 100 problems is very difficult. And part of the reason is the way that traditional predictive analytics is carried out. If we look at the top half of this diagram here, we can see this is the way that we see traditional predictive analytics. So you can see the end user has a problem, such as, I want to predict when my compressor is going to fail next. I want to predict when my production is going to be lower than expected, or I want to predict my next flaring event, for example. So the end user has a specific problem that they want to solve. They send that problem to a data science team, and the data science team will go away and look at the data. They'll engage subject matter experts, and they'll build a number of models to try and model that or solve that particular problem that the end user has. What we find is that this process generally takes in the order of weeks or months. So 3 months or 6 months to solve one of these problems is not unlikely, or it's not unheard of. And once they've solved that problem, they'll then deploy the solution back to the end user. So the end user has a problem, they send it to the data science team. 3 months later, they get a solution. The solution will be fantastic and it'll be fit for purpose, but I guess it's the time frame that we're concerned about in that traditional workflow. So 3 months per problem, you can imagine how long it's going to take to scale that to 50 or 100 problems that your facility might want to solve. On the other hand, VROC's taken a different approach to the way these predictive analytics problems are solved. So through VROC's platform, which is the bottom half of this diagram, the end user has the same problem. They want to predict when their compressor is going to fail next, when their next flaring event is going to happen, et cetera, et cetera. What they can do on the VROC platform is then go through a number of wizards which will guide them through providing the information to VROC that the system needs to solve that problem. So the VROC system will ask questions that any engineer or subject matter expert will be able to answer just by virtue of their job. Once VROC has asked all the questions and has the sufficient information, it can then go away and automatically model that problem. So VROC will take the problem that the user has specified, it'll build hundreds or even thousands of models in the background, it'll look at the problem from different perspectives, it'll use different modeling techniques, and it will try and build a model to solve the problem that end user has. The beauty about an automated system is that instead of that taking 3 to 6 months, that can be done in half an hour or an hour. So end user has a problem, they type the problem into VROC, they say, okay, please solve this problem for me. Half an hour or an hour later, you can get an email back from the system saying, this is the problem you asked me to solve. I've been able to solve it with, say, 95% confidence, and here's the solution. These are the important factors, and this is what the solution looks like. Do you want to put that problem into production? And the end user can click yes, and then as new data comes in, that problem is now in production and is now providing them real-time insights. So we're really trying to speed up that whole cycle of specifying a problem, building a model, and deploying these solutions for our clients. The beauty about the solution is that it's accessible to anyone. So you can have your mechanical engineers, you can have your electrical engineers, you can have reliability engineers, your process engineers. They can all be building models and modeling different parts of your facility to keep an eye on them and avoid undesirable events from happening. So you end up with this huge number of models that are all monitoring the different parts of your process all at once, identifying things that need to be done before they actually cause a problem and before they cause any significant downtime. So that's the theory, and that's the system that we're trying to develop, or we have developed and deploy. Of course, it's an automated system, so we're not going to be able to solve 100% of problems with it. We find that generally about 80% of problems that people want to solve can be solved using the automated modeling technique. The other 20% of problems, if people still want to solve those problems, they can still be solved, but they'll go through the manual modeling, traditional predictive analytics path of solving it using data scientists and subject matter experts, because we might find that we do need some additional sensors to solve those really tricky problems. But the idea is to solve 80% of the problems, to solve the vast majority of problems very quickly and get return on investment for this type of technology very rapidly. Okay, so now that we know more or less how this technology works and how it's deployed, I'm going to take you through a quick demo to show you how it actually works in practice. So how we build the models and what we can do with the results. So just give me a second. I'm just going to share my screen. Okay, so hopefully you can see that. That's right. So this is a mock-up of one of our model wizards. So this is what our model wizards look like and what anyone as an end user would see. And you can see here, I've got a couple of use cases here, which are just typical use cases. These can be customized and modified depending on the type of facility or the type of problems that the client needs to solve. But you can see if I want to predict when the next failure or undesirable event will occur, I can use this one. Predict what a value will be in future. I can use this model. And again, we do a lot of future value predictions, so predicting 4, 12, 24 hours into the future. So you can tell what a process parameter will be in the future based on what's happened in the past. Identify the root cause of an event. So if we've had a specific event happen on the plant, we can run one of these models to identify what was the root cause, what actually caused this in the first place. Identify when equipment or process is degrading or not operating correctly, or predict when equipment maintenance is required. So these are 5 typical use cases that most people want to solve on their facilities. So if I just click through one of these, I'll just go through the top one, which is predict when the next failure or undesirable event will occur. So I can go through that. Now it's asking me what would I like to call the model. I'll just call it my equipment value model. There we go, we can give it a name. Select the folder you want to store the model in. So we can obviously store it in folders to keep our models organized. So I'll just store it in a general analytics folder that we've got. There we go. Now, because I've selected a model that's predicting a failure or undesirable event, it's asking me how can I tell what a failure looks like. So we have to be able to tell it, what this undesirable event looks like. And again, this can be as simple as complicated as you like. This can be free-form calculations. It can be multiple conditions. What we're going to do today is we're going to pick a sensor. We're going to pick a gas compressor speed setting, ANNGP, and I'm just going to go back. I think we've got data from a few years ago for this one. Here we go. Here's some data for this particular sensor. We'll just zoom in on this so you can see what's going on. All right, cool. So this is a gas compressor speed set point that we've got some data for. And so we can see when this compressor is running, our speed is in the mid-90s, 94, 92. 98. And so what we want to do in this model, this will be a very simple model. We just want to predict when the next failure will occur, when this thing is going to shut down next. So we'll say, we've got a threshold here. We'll say when the value of this sensor is less than 80, let's say, we'll call that a failure. And you can see we've drawn a line there now. So we can see whenever the sensor drops below this yellow line, which is the 80, that's considered a failure. Again, this is a very simplistic example. These can be very complicated, these conditions, or they can be very simple depending on the type of problem you want to solve. Okay, so we specified our failure criteria. We go next. Now it's asking me to select an optional condition when the model is active. So for some pieces of equipment, maybe you take them out of service for maintenance, maybe they're not always running. We can give the AI a bit more information about when this piece of equipment is actually in service. So if we want to, we can select a specific tag or condition there. We can do a free-form calculation. We can do a number of conditions there to let the AI know when this piece of equipment is actually running and actually in service. For this one, I'll skip this. We don't need to use that. We'll skip that one. And now in this step, we can select specific input features. Now, this is useful, for example, if you're trying to predict something that's happening topside on your platform, but you only want to include the features for your subsea equipment. So I want to know what's causing sand or moisture topside, but I only want to look at what happens subsea that's resulting in this undesirable condition topside. I can limit the input features here to say, only consider the subsea factors when you're trying to predict this particular failure. Again, for this model, we can leave this blank, and VROC will decide what the useful features are for this particular model. And so that's all we need to do. Now it says, are we happy with the settings? So we're going to predict when the next failure or undesirable event will occur. That's the name of my model, my failure model. That's where I'm storing it in the tree. My predictor is this, the GCM1 NGP, GCM1 speed of the compressor. My threshold is when it's less than 80. So whenever it gets less than 80, that's my undesirable event I want to prevent. I've got a prediction of 7 days. So I'm going to try and predict this event up to 7 days in advance. We can change that if we need to. The activation, we have ignored that. So the model will always be active. And we haven't refined the input features. So VROC will go through all the data that's available from your platform to work out how to build this model. And so what I do next is I hit train. I won't do that now because this model might take half an hour to build. But what will happen is when I hit train, VROC will go away, take that information I've put in there, and it will gather all my data that I've got, my last 2 years worth of data, and it will try different techniques. It'll build hundreds of models to look at this problem, to try and solve this particular problem. And at the end of that, as I said, an hour later, you'll get an email coming back saying, this is the problem you asked me to solve. You wanted to solve this GCM failure model. I've been able to solve it with 95% confidence. Here's the information I used to solve it. Are you happy with that? Do you want to put that into production? And you can select yes or no. And if you select yes, then obviously you have a real-time streaming AI model monitoring your compressor from then on. So that's basically all you have to do to build models. And as I said, it's very simple. So all your subject matter experts, all your engineers can build as many models as they like whenever they need to. And you can have hundreds of models running on your facility, looking at various aspects of it to ensure that you're maintaining reliability and maintaining your optimum production rates. Now that we've built the model, let's have a look at what that actually looks like. How does that actually help us? So I'll just switch over to another screen. Just give me 1 second. We'll just change over and we'll show you what this actually looks like in practice. Okay, here we go. All right, so hopefully that's come up for you. So this is one of our dashboards. They're all drag and drop user configurable. And so this is for 3 pumps, a real problem with 3 pumps that we've completed a while ago. And you can see up the top here, we have this row is pump A, below it we have pump B, and the bottom row is pump C. And this is over a 10-day period, this trend. And you can see pump B and pump C are all green, which means they're all healthy. Pump A, we're showing some mild degradation here to yellow. And then we're showing some more severe degradation on the right here, which is shown in the red. So basically what the AI is saying is that pump B and pump C are fine. I'm seeing some significant degradation on pump A that needs to be looked at straight away. And so now that we see this, what we want to do is drill down and work out, what is the degradation in pump A? What do I have to do to fix this? So we'll drill down to the second level for this one. So this is the second level for pump A we're looking at now. We'll just wait for this to come up. It should take a second. Here we go. And so what we're seeing here are the major components, I guess, of pump A. This is what we call our DNA map. So over the same time period, 10 days. But you can see each row here is a different component of pump A. So we can see at the top here, we've got our non-drive-in vibrations, we've got our drive-in vibrations, our non-drive-in temperatures, drive-in temperatures, pressures, levels, motor current, etc. And so what's actually happened here is VROC's gone through, and for each one of these, it's identified these, and it's built a model to try and work out under all different operating conditions of your facility what the expected vibrations and temperatures of this motor should be. So it's looked at your historical data and analyzed it under all different operating conditions and said, this is what I expect the vibration to be based on the way that we're running at this very point in time. and it's calculated that, on an hourly or minutely basis, depending on how often we're getting new data. And what it's done then is compared its predicted vibration to the actual vibration to see if it is actually performing as it expects to be performing. And so when there's a deviation, there's a difference between what the AI predicts the vibration should be and what the vibration actually is, then we get these color changes into yellow or red. And you can see here that the AI has identified these two rows as red, so significant deviation, and those correspond to the drive end bearing vibration. So at this point, there's a problem with the drive end bearing or around the drive end bearing. So you can go away and do some inspection on the drive end bearing if you want at this point. Alternatively, you can drill down further to the third level, and this is giving us now more information about the problem. So we can see at the top here, we're showing the same degradation graph. We're showing the mild degradation and the more severe degradation. The bottom graph here is showing us what the AI is picking as is driving that degradation. So we can see here, during the mild degradation period, we have one set of features. As we move over here to the more severe degradation, we can see the change. There's a very visible change in the graph here where this red section is a lot more prominent. And so this red section these are actually all actual sensors that we're getting data for. This red section corresponds to the mechanical seal leakage flow in this particular example. So we know that the mechanical seal leakage flow is a significant contributor to this particular failure. And so what the AI is telling us now is that we know there's a significant degradation on pump A. We know that the degradation is due to or is related to the drive end bearing. And we know that it's driven by the mechanical seal leakage flow. So essentially what this is telling us now is that we have a mechanical seal degradation or impending mechanical seal failure on this pump A on the drive end side. And so now what you can do is you can switch over to another pump, you switch over to pump B or pump C, and you can then repair this pump's mechanical seal before it suffers a catastrophic failure. And so that's how this AI works. It works by identifying components that it sees as degrading or not performing, and it provides you all the information that you need to be able to very rapidly identify what the root cause of the failure is and to take some action before the failure becomes catastrophic and causes you significant damage or downtime. Now, for this problem, this is the first time that any of these pumps have failed on this particular facility. So they've had no failures in the past. So there's been no previous failures for the AI to learn from. If there were previous failures, then it would have been able to provide even more information about the expected time to failure. But for this type of problem, because we haven't seen any failures, all we can identify is the degradation. And so in this case, the client successfully switched over to another pump and repaired this mechanical seal and restarted this pump shortly afterwards. So that's sort of how the workflow with this sort of technology works. So I'll just quickly show you now how it's deployed. So to deploy this sort of technology is actually extremely straightforward at the moment. Can be done completely remotely. No one needs to be on site. We don't need to attend site at all or even see the facility. Generally what happens is on the client side, they prepare the historical data, which we can assist with, and set up streaming of the real-time data. So usually this is what takes the most time, is organizing the supply of data. After that, we ingest the historical data and commission the real-time streaming. That could take a week, it could take longer, it depends on how we get the data, but generally we'll say a week. After we have the data, we can then do some client training workshops, and we can start actually building some initial models there. So we can start doing some initial modeling there and show clients exactly how to do it themselves if they want to do that. After that, you should have some models in production already, and then it's just a matter of ongoing training and support. So again, with this sort of technology, there's no additional sensors required, as we mentioned earlier. There's no lengthy setup process. Data ingestion can be very simple. Sometimes getting the historical data is difficult, but it's not unachievable. It happens, we do it for every client, so it's fine. And we can manage this in a 4-week turnaround time to actually get some value from this technology up front and start reaping some of the benefits. So I know it's been very quick and I've gone through quite a lot of content there, but if anyone has any questions, if you could put it in the chat, I'm happy to look at answering some of them now.
That's great, Trevor. Thank you very much for going through that so quickly. We have had a couple of questions in.
Okay.
The first one being, and I guess it's very apt at the moment, it says, you mentioned being able to manage this solution remotely. How easily will it be to implement VROC during the COVID-19 lockdown?
Yeah, I mean, it's fine. We actually, again, what takes the most amount of time is connecting to clients' data centers, connecting to their data. So as long as we can get access to their data, that's fine, because generally, there'll be a VPN or some other type of secure communications connection set up, and that always happens remotely. So yeah, the actual setup of the data ingestion happens remotely by virtue of the fact that there's no other way to do it, really. The client training and the initial modeling happens via video conference, which we do all the time. And so really, the fact is that it's all served up by a web-based dashboard, so there's no software to install. It's a very quick and easy process. So for COVID-19 and for people working at home, this is a very easy solution. And once the IT, I guess, connection is sorted, then the rest of it is pretty much straightforward. And as I said, 4 weeks is definitely achievable.
Okay, great. Other question. Can different people within an organization have access to certain parts of the system to others, i.e. engineers see the technical data and say the director level have just like a general overview of the results?
Yeah, sure, that we do that all the time. And again, that can also be integrated into clients' existing reporting systems if they want as well. So if you have Microsoft Power BI or other reporting software that you use for your management level reports, you can actually suck some of the data out of VROC and display it in your Microsoft Power BI management level report. So that's something that we do quite often. It's also possible to chain models. So VROC automatically uses the data from all the individual models to build overall models. So management might only care about, the performance of my platform as a whole. So you can build a model that will suck up all the data from all the individual models, monitoring all the different bits of equipment, and tell you overall how your performance, the performance of your platform is. So definitely, this idea of hierarchical information is something that we always implement on all our solutions. So the high level is a very basic, high level view of what's going on, what piece of equipment do I need to maintain, and if you're more technically or you're a more technical person, you can drill down and get more detailed information to really solve the problem and identify what's going on there. So yeah, definitely the hierarchy of information and the openness of the system allows both management and engineers to have a view of the same data that's relevant to themselves.
Great. How long would it take to implement this system on a typical offshore asset?
I think usually what we find is the most amount of time is taken up by actually the client exporting their data. So once the data is exported, as I said, it's only generally a few weeks. So exporting the data and going through the security precautions to set up the VPN or secure communications is usually what takes the most amount of time. Once that's sorted, the rest can happen very quickly. But getting that initial data exported and getting the IT permission to set up the secure connection is usually what determines how long the whole exercise takes, as that's usually an order of magnitude longer than the actual rollout of the VROC system. So, but as I said, 4 weeks is definitely achievable if we can get buy-in from everyone and get the right permissions at the very beginning.
Excellent. And you mentioned earlier about the results are generated and sent back to the customer. Do you actually require, for example, an in-house data scientist to be able to review and analyze these results, or are they available for anyone to read and make sense of?
No, it's designed to be run by end users. So it's designed for engineers to use. So engineers can go in and build the models. Engineers can interpret the results. As I said, this will work for 80% of problems. For the other 20%, if you want to solve them, then you may need a data science team in-house, or we can assist with that as well. But the system is designed to be used solely by engineers. So no data scientists are required to make use of the software.
Okay, what is the difference between VROC and the OSIPI alerts?
Yeah, so I guess the difference, I guess, is VROC is AI. So VROC is actually learning how your facility works on a sort of a broad scale. So we're looking at all the data across your entire facility to build very accurate models about how each piece of equipment interacts in that whole ecosystem that you have. It's not sort of a condition-based or alarming system where you just look at certain aspects. So we're not just looking at one pump in isolation. We're looking at how that pump operates in the context of the whole operating platform. And I guess that's the key with using this AI and big data technology, is that we're able to build very specific models about individual pieces of equipment and how they respond in relation to the whole asset. So obviously each piece of equipment doesn't work in isolation, and being able to model how that piece of equipment works in the context of everything else is really where you get the power from this sort of technology.
Fantastic. And just one final question we're going to sneak in there, because I know we want to try and limit this to 30 minutes. If we don't, for example, if a customer doesn't have the right amount of sensors or is not getting enough data for us to analyze, are we able to install additional sensors to get that information?
Yeah, so what we find typically for oil and gas production platforms, they have sufficient sensors because they usually were very well instrumented just from a safety point of view. If there aren't sufficient sensors, then yes, we can install, low-cost wireless IoT sensors that monitor certain parameters. So if you want vibration or acoustic or temperature transmitters, we can install those on the platform, and they're very low cost, and they provide just the right amount of information to be able to use this sort of technology. So generally we find maybe drill rigs have less instrumentation than production platforms. So for drill rigs, we have a drill rig package where you can install sensors on your mud pumps and top drives and bits and pieces like that, generators, and provide just the right amount of information we need to use this sort of technology. And again, those sensors are very low cost. They attach very easily. They've just got a battery and wireless in them, so you don't need to run any cables, and they're a very cost-effective solution to try and deploy the solution very quickly.
Excellent. Well, I think we're going to aim to wrap things up there. Now we're on the 30-minute mark. So thank you very much, Trevor, for taking the time to go through this for everyone. And thank you, everyone, for attending. We will be sending out a link to everyone that's logged in with a recording of the webinar so you can review again and pass on to any colleagues that may not have been able to attend today. But if you do have any further questions, then please continue to send them through and we will get back to you as and when we're available. Thank you all very much. Thank you.
Thank you.